you very much to the organisers for the chance to speak here, and thanks to Frank for this lovely beginning overview for surgery theory. I'm really looking forward to talking in this summer school. It's a large picture, and I'm going to fill in some details. So if you're going from the big picture from Frank, if now you really want to see some specifics and apply surgery theory one manifold at a time, see what happens. Well, this is an example of that. So this talk is in the direction of a research report. So this is all joint with Johannes Nordstrom. And a little bit later on in lecture 4, the material will also include Sebastian Goethe. So I'll just say that from the beginning, this isn't part of a joint project. So what's my category? If I keep things simple, for the next 4 talks, M is always going to be a closed, smooth, spin 7 manifold. 7 is a great dimension. You know, it's low enough that you can build explicit examples and you can see it. It's high enough that the full power of surgery is available. Geometrically interesting examples arise in dimension 7, so it's a very nice playground and it's a good place to work. And every homeomorphism or diffeomorphism I write down is going to preserve the spin structure, unless I say otherwise. So my category is the spin category. Okay? Just make that clear from the beginning. So what am I interested in? This is almost back in the pre-surgery theoretic days. I'll use the 2 to indicate connectedness. So I'm interested in the diffeomorphism class of these guys where M is 2 connected. So pi 1 and pi 2 vanish. Now there's room for a third homology group. And one of the things I'm going to report on is an algebraic classification of this guy to an algebraic category. So this is totally algebraic category. Q spin. Okay. So that's one thing I'm going to tell you about. This will be a classification. And in fact, the methods here are pre-surgery theoretic. If you wanted to try and set about and do this, you shouldn't first classify them up to homotopy and then go ahead. It's not the right way to do it. These manifolds are simple enough that handle bodies and other techniques are the right way to go. Yeah, I'm going to fill this in here in a moment, but let me go on. So what are some of the key players going to be in this game? So in some sense, you could argue surgery theory was in part invented to understand the homotopy 7 spheres. So these will be the 7 manifolds that are homotopy equivalent to S7. These form a group under connected sum, and that's Z28. So now if you really want to classify all of these manifolds or other 7 manifolds, you're going to have to come to grips with the following guy, that's the inertia group. So if I have a random 7 manifold, it's not always the case that if I take connect sum with the homotopy sphere, I change the smooth structure. It could be, from a point of view of inertia, things just stay the same. And yeah, you might have a classification up to almost diffeomorphism, connected some with homotopy spheres, so now you're going to have to understand this group. And it actually turns out that getting to grips with this group in specific examples is a very subtle problem, and it's a problem that surgery theory, classical surgery theory, quite struggles with. I would say. So,
are you requiring that the equivalence be homotopic to the
everything's oriented, right? Everything has a spin structure.
No, M connected sum sigma.
Oh, this is a diffeomorphism here.
But it's
so this
not
is
the end of the
No, that's right. So we introduce that in a moment. In fact, that'll be an exercise. The homotopy inertia group was surgery is very good at understanding the homotopy inertia group, for example. Yeah. Yeah. And hopefully at the end of this talk or next time I'll give examples where the homotopy inertia group and the actual inertia group are different. Yeah. Okay. So here are some of the stars of the show that will be appearing and that we'll need to come to grips with. I should have said, by the way, that what I'm doing right now is an overview of the 4 lectures I'm going to use. So let me jump ahead. It won't be relevant for the rest of today's talk, but let me just tell you a little bit about G2 topology, or what I mean by that. So G2 is the group of automorphisms of the octonions, and you can think of it naturally as a subgroup of spin 7, but it's simply connected, so that it's in fact also a subgroup in SO7, the double color. And so manifolds with G2 holonomy, so what's that? So I'm going to mention briefly now, this is going to be a Riemannian manifold. So this has full holonomy G2 if the group generated by parallel transport, I'll say that in a second, is equal to G2. So now I have a metric. If I pick a loop in my manifold, maybe it goes around some topology, parallel transport along that will induce an orthogonal transformation of the tangent bundle at that point. And so that's this T gamma. So a priori, the holonomy of a Riemannian metric sits inside of the full orthogonal group. And if you work very, very hard, sometimes you can get special holonomy. And special holonomy, for example, in the group G2 can only occur in dimension 7. Theorem of Berger. Some people think the universe has got 11 dimensions and that the other 7 dimensions are a singular G2 manifold. So people interested in M theory and so forth, there are other motivations outside of the intrinsic beauty of this to study these sorts of spaces. So moduli spaces will be a theme in other talks. So I'm just going to write MG2 to be the moduli space. Suppose I have a G2 holonomy metric, they exist. It's very hard to build them, but they exist. So I'm going to call this the moduli space. One thing that's a completely open problem in G2 topology is whether this moduli space is connected or not. It's an orbifold of a known dimension, but up until recently there was no idea whether this was connected. So with Nordstrom, we introduced what we call a topological moduli space. So if you want to forget, there's a G2 holonomy metric will induce a G2 structure on the tangent bundle, just in the same way that you have a spin structure. So literally your tangent bundle has a frame bundle, and you reduce the structure group of that frame bundle down from SO7 into G2. And then you choose structures of them in the usual way, so I'll denote that by M phi. And there's a very natural way to make this into a moduli space. So you can talk about the topological moduli space. So, this is the real one here, and this is the topological. And what we did with Nordstrom was we first defined an invariant from here out to Z modulo 48. And
surjective?
Surjective, not quite. It's 24 of the 48 elements.
Not zero.
Not zero. Not zero. Yeah. Not zero. Yeah. Thanks. Yeah. That's yeah. Not zero. Yeah. It's 24 of these 48 guys. And what I want to say is I won't have time to define it. I just want to introduce the word to try and connect these two ideas. So we're going to introduce an integer called the reactivity event. I'll just say it if you take, I'll just write it down in words. If you take a mapping torus, so F is going to be a so-called almost diffeomorphism. So that's a diffeomorphism of M, except maybe at a singular point. But the mapping torus of that thing still has a Pontryagin class, and you can take it square. And if you look at all the possible values that you get from this mapping tori, this will be, right, so what's the right way to say this? Lives in here. Okay? So you look at all the possible values of p squared of this mapping tori that you get for every almost diffeomorphism you can imagine. That will be some subset, in fact, some subgroup of the integers, and this reactivity, as we call it, is the non-positive, non-negative integer that defines that subgroup. We call it reactivity because to understand reactivity is what you need. It's the opposite of inertia. We didn't have a great name for it, but somehow the opposite of inertia, and that would be activity. So, yeah, so let's see. Actually, what I said was not quite right. This new invariant is a new invariant on pi naught of the moduli space. And here we need, so to fully compute this, fully understand, we also need the reactivity of M. So that's a connection between the two branches of the talk is going to be this concept of reactivity needed for both inertia and to understand the number of connected components in a topological G2 moduli space. So that's basically a plan of lectures 1, 2, and 4. And in lecture 4, I'll tell you about work that Goethe and Nordstrom are doing. So this picture gets complete. This invariant isn't defined here, it's not topological, but the invariant was discovered from a topology. And in lecture 2, in some sense, stands off a little bit to the side. This is where I'm going to talk about one connected 7 manifolds. So there, I said in my abstract, if you look at simply connected manifolds, they're classified up to dimension 6, modulo the wild dimension 4, but up to homeomorphism, that statement is true. And in dimension 7, this is the first dimension where we don't know the homeomorphism classification of simply connected 7 manifolds. So I wanted to say a little bit about how we might approach that problem.
A question about your examples on the topological modular space. Do these come from honest G2 structures in the sense of a Riemannian matrix?
Yeah, well sorry, this M phi is a certain 3 form. So this moduli space can be thought of as a space of positive 3 forms. So they all give you a metric. It's just whether it's torsion free or not is a question of whether it goes to full holonomy.
Okay.
So in this case, you can think of this as a space of a certain class of metrics. Those metrics defined by positive 3 forms.
But the question of the nu hat, if you know that nu hits 24 elements, we would know that nu hat also hits if we knew all these elements in particular.
No, that was the whole problem. So the whole idea was to disconnect this moduli space, right? And yeah, so what I'll announce, Goethe and Nordstrom have announced that they can now do that using this invariant. So the motivation was that in Imperial there were tens of thousands of manifolds being built, and 2 connected manifolds, very simple ones. And so you could now compute this. So then Nordstrom and I proved that for all of the guys that they could build, you got 24, which was a bit disappointing in terms of disconnecting the modular space. But then, inspired by this invariant, Goethe invented the new hat invariant, and you thought maybe you can hunt more, and then they proved that even the new hat invariant was always 24 for all of these guys. And then they went away and built even more complicated examples, and then finally got something where the value of nu hat, they can now get different values of nu here. But to do that, the computation goes through this nu hat. That's a long answer to your question. Yeah, okay, so that was an overview, and actually the G2 stuff won't appear until Thursday.
Excuse me, just to get this, on the moduli space, the action of the diffeomorphism group is already...
Yeah, modded out, yeah. I mean, diffeomorphisms here mean spin diffeomorphisms. Yeah. But the full group of spin diffeomorphisms. Yeah, so just to finish this picture off, overview. In fact, one of the outcomes of this is you can look at a category of G2 manifolds. This is just topological, okay? And there's an obvious forgetful map, so this is this category of these M phi. But now we'll also ask that M be 2 connected. And we also get a complete classification of this. So there's a QG2 going to some another algebraic category. And we actually get a complete classification of the G2, topological G2 category as well for 2 connected manifolds. It was a little bit of a surprise when that came out, but it did. Okay. So good, that's the overview. So now...
So these G2 manifolds, they come with metrics.
They
should be, the right-hand side is supposed to be quite big, right?
Yeah, I mean, this is up to diffeomorphism. So this is actually an extension, and in some sense, the right way to say it, there's a Z acting here on the fibres.
Not more.
Not more. No. The number of G2 structures on any given spin 7 manifold is up to homotopy is just a Z. And so what we do is actually work out exactly this Z sometimes acts trivially and sometimes not. So we work out exactly what the fibres are. But this is a statement, this is still a weak statement because we're classifying up to homotopy and diffeomorphism.
And every spin manifold has a G2 structure.
Every spin manifold has a G2 structure, which matters on. Yeah. Okay. Alright, let's see how this goes. I don't think I've mastered the Munster blackboard technique. But let's start here. Homotopy spheres. So these were mentioned in Frank's talk. I'm just going to give you the theorem that we need for this is Crowley and Milner in 1963. And I'll state this in modern notation, try and use Frank's notation. We have the relative boundary normal invariance of S7 cross I. This maps to our friendly LH group, which maps to the diff structure set of S7. So this is what I call theta 7. And then this maps to the differential normal invariance of S7. So this guy here is a Z given by the signature. So this is a collection of even quadratic forms. So if you like, you can think of it as 8Z. Because the signature of an even non-singular form is divisible by 8. This group here is uprisingly 0. So if you know this stuff, this is pi 7 of G mod O. And the thing to say is that the J homomorphism is 0 in this dimension. So that's nice. No exotic spheres to worry about. And what Crowley and Milner proved, well, this group here was going to be a Z12, which point, and this guy's here, and this map is multiplication by 224, which is 8 times 28. So that's the 28 I have it for. Okay, so this was one of the early triumphs of surgery theory, and that's how the surgery exact sequence for the 7 sphere looks. So just a remark here, what you had to know, so we needed to know the minimal signature of here. So these manifolds here, on one side you can cap it off with a standard atheist, on another side you can try and cap it off. And so the manifolds here, the closed manifolds here will be so-called almost parallelizable. The tangent bundles will be trivial if you remove a point. So we need to know the minimal signature of a closed, smooth, almost parallelizable 8 manifold. I'm emphasizing this now because when you apply surgery theory, understanding surgeries will give you some algebra, and then to actually apply this to manifolds, you have to know the value of your invariance realized on closed manifolds. It's just absolutely fundamental. So in all of these computations, using actually the fact that you knew the J homomorphism here from Adams's work, then you could actually go back and work out what the minimal signature was here. So just to emphasize that, if you want an invariant of a 7 manifold, you need to know the value of your corresponding invariance on 8 manifolds. Okay, that's good. So what about an invariant that would see this? Suppose someone gave you a random homotopy sphere and said, is it standard? Or suppose someone gave you 2 manifolds and said, well, they just differ by connected sum of the homotopy sphere. How would you tell them apart? Okay, so this is the L's hyper invariant. So I was actually recently in Utrecht and drawing up in Australia, I called this the Eels-Kuiper invariant, yeah, which is completely wrong, so it's Eels-Kuiper. Anyway, and in 62, they constructed there's this an invariant, and I'll define it presently. It's called the mu invariant. It goes from theta 7 bijectively into Z.
Excuse me, so concerning your remarks, so is the minimal signature really 224? Then?
Yeah.
I mean,
Yeah.
you can really write down a manifold which has signature 224.
Yeah, you have to use, this is one of these things where you rely on the computation. You don't, the state, once you know the stable homotopy theorem, you know the J homomorphism in dimension 7, and you know the signature theorem, you just turn the handle. No one, so far as I know, no one, it's probably not the case, but that manifold appears in nature.
You would have to know a reason, so that the element in the kernel of J, you would have to know a reason why the J of it is 0. And with some correct manifold is
It could potentially be that we have a construction which
yeah, maybe, but
So the definition of mu, so here's a nice, how does this go? So Milner proved that the spin Boyden group is 0. So if I take my sigma 7, I can make it the boundary of an 8 manifold. So spin 8 manifold. And the Eels-Quaker invariant is a defect invariant, so just emphasizing this point about knowing invariants for closed 8 manifolds. So we'll come to that in a moment. We're going to exploit the fact that the A-roof genus is an integer. So you define mu of sigma. So there's a certain Pontryagin eigenclass associated to this manifold W. You can take its square, you take the signature of W, and you divide by 8. And you think of this now is well defined in Z128Z. Okay, so let me tell you a little bit about the ingredients of this. So what's this PW? So the fourth cohomology of the spin integral, all cohomology is integral unless otherwise stated. That's a Z, and the generator here is called P. It's halves the Pontryagin class, so 2P is P1. Okay, so there's a canonical map in the fourth cohomology of DSO. The first Pontryagin class is here. So spin manifolds get this extra divisibility for you. And so you get this cohomology class for any spin manifold. How do I take the square of this here? This looks like a cheat because I've got a class in the fourth cohomology of W. Its square is in the eighth cohomology of W. W is a compact manifold with boundary. There's nothing in eighth cohomology. So this is a classic cheat. In this sequence we're going to be looking at more often. So for a homotopy sphere, this map here is an isomorphism, because the other groups here I'm going to put in would be the, this is going in the wrong direction. So this is an isomorphism. We don't really need that it's an isomorphism, we just need that it's rationally it hits this class. So here's P of W, we take P of W and lift it. And then I'll just put this in here. P squared, P squared, evaluator on the front end. So that's good. Now we've got an invariant. Let me just say a little bit about make some remarks. Oh, now I need a lemma that I'm going to use later on. Sorry. So yeah, I just want to tell you a little bit more about this spin manifold, this spin characteristic class. So EM. Using 2 as for of M. Remember, M is always, so this is true for any closed spin manifold. These are facts I'm going to need later there. And also, P sub W is characteristic for the intersection form. form is going to play a key role in what follows. If you reduce mod 2 coefficients, the generator here is the fourth Steeple-Whitney class, which is the same thing as the fourth Lou class. The fourth Lou class tells you about the square 4 operation. In an 8 manifold, the square 4 operation is the squaring operation. So that's why, what this means is characteristic. So that means I need lambda W of x, dw of x, all x. So there's this beautiful feature about spin. It's a little bit like spin C in dimensions 3 and 4, that this Pontryagin class is correlated to the intersection theorem. That's a fact that we're going to be exploiting a lot in the next half an hour. Okay. Yeah, and let me just now make just a couple of remarks about the Diels-Kuiper invariant. So the A-root genus of closed spin 8 manifold, this is the same thing as the index of the Dirac operator X. Okay. So if you know what these words are, that's good. If you don't, maybe others will say something about that. And then Herzog will tell you that the A-root genus is some polynomial that I don't really want to write down now in P2. Okay? So it's a linear combination of these things. And Herzog will also tell you that the L polynomial, which computes the signature, is a different polynomial. Okay, probably more primes so the P, if you're looking at this W, P2 is bad because W doesn't have an honest P2, so you eliminate it and you get an equation for the A-root genus that only involves P1 squared and the signature. W's got a signature. And then you say this has to be an integer, and so you get a defect invariant. That's what's going into this Diels-Kuiper invariant. So the slogan, what's that? U is the defect. And as a consequence of that, if you know that the Tier-Singer theorem, that means you can give an intrinsic definition of mu.
What do you mean by defect?
Sorry?
What do you mean by defect? Defect of what?
It's just in this sense. There's a theorem that tells me the A-root genus of a closed spin 8 manifold is an integer. Then that gets expressed in terms of the rational, these are rational coefficients I should say, so they have denominators. So the fact that the A-root genus is an integer gives me an invariant of 7 manifolds by looking at boundaries and trying to compute the A-root genus. For example, if my homotopy sphere here was the standard sphere, I could just cap it off with a disk. I would get a closed spin 8 manifold, and whatever number I computed would have to be the number you get for a closed spin 8 manifold. That's what I mean by a defect.
But somehow you ignore the P2 sum.
You eliminate them. You use these two equations to express P2 in terms of P1 squared and a signature. When you use this. I express P2 in terms of P1 squared and a signature. And then P2 is gone. And so A hat just becomes an equation in P1 squared and a signature. And W has a P1 squared under the assumption, and W has a signature. So those two things, this is Milner's insight. This is how he used an invariant called the lambda invariant, and he just used the L polynomial. Okay. Here's the slogan. Let me just make another remark. So mu of m defined. All we used in the definition is the rational vanishing of this Pontryagin class. So if I now look with rational coefficients, all I had to do to make this definition was to, see this is, by naturality, this is going to go to the Pontryagin class now. So all I had to do was rationally lift this. So if this thing is rationally trivial, I can rationally lift this and everything else goes through. So to define this Diels-Kuiper invariant, all I needed is actually this. And a consequence of this slogan is that you can get an intrinsic definition. So you can actually write.
I'm a little confused. You have M, W. What is M? What is W?
M is always a 7 manifold, and W is always its co-boundary. So W is a spin 8 manifold.
M is boundary.
Yeah. This is W8, and okay, to begin with, this is sigma, and then we can replace sigma by an M.
You take another Bordism, when you do this, it had everything, subtract the signature and one square.
I mean, yeah, this is linear algebra, so I wanted to avoid doing linear algebra in the blackboard. So what I was saying, this remark, is that this new invariant can be expressed in terms of the eta invariant now of, this is true whenever this is defined, this is the Dirac operator M. So this is eta invariant. It's a measure of spectral asymmetry, I don't want to talk about it, but the point is that it's intrinsic. It's a little bit annoying if someone gives you a random 7 manifold, they typically don't give you the co-boundary. Okay? So you can use abstract reasoning to say that if there is a co-boundary, you get an invariant, but if you really want to compute in hands-on examples, you want an intrinsic definition. So that exists for the Steele-Twycke invariant. Okay. Right, it's probably a good opportunity to clean some boards. Okay, so to summarize, dimension 7 we have some interesting manifolds, 28 exotic 7 spheres. If we want to carry out a smooth classification, we have the problem then of detecting the action of these homotopy spheres. And under this assumption, we have an invariant that will do that. So that's a reasonable start if you wanted to carry out a classification. Now you could attempt to classify up to connected sum with homotopy spheres. So that's called almost diffeomorphism. Oh, okay. Actually, while I'm here, before I move on, since I wanted to include some explicit examples, let me do that. And we'll be using these guys later on. So there's a very nice class of 7 manifolds which arise as bundles. So these are linear bundles, 3-sphere bundles. And how's the notation? So these are, this is the sphere bundle. So the bundle. And so this, the Euler class of this bundle is by definition N. And the Pontryagin class, the spin Pontryagin class, by definition P. This characteristic fact means that the only condition that we have is that these two numbers have to be equivalent modulo 2. But other than that, you can write down any bundle like this. And if you so if you now look at M13, the fact that we put a 1 here, when you go through the homotopy sequence of this vibration, you'll see that pi 4 here maps isomorphically onto pi 3 here. That's what the Euler class does. So that will make this total space here a homotopy 7 sphere, and you can compute this mu invariant and you get 1. And you notice that 1 is not the same thing as 0, which is what you get for the 7 sphere. So this was Milner's first example of exotic spheres. A very nice explicit manifold. you have to prove, this was, Milner could use Morse theory, you then have to prove, it's clear that this is homotopy equivalent to the 7th sphere, but then using Morse theory, Milner could show it was actually homeomorphic.
So, sorry again, so for a general M, your invariant U of M, where does it live? Because you say using that it's rational, so it's 28. What?
Yeah, you got me, thank you. So the general mu of M, this is a very important point. It's going to lead into modular. So out of this process, you cook up a priori a rational number.
And now suppose that M itself would be string, let's say, so Pn itself is 0, not only rationally 0, so then we can improve this to an integral thing.
No. So it's the fact that it's when you have a homotopy sphere, that's constraining that you live in Z mod 28 Z. It's not the fact about Pm.
Okay, so what happens if Pm is 0 itself? What special values do you get? Can you say something?
It's hard to say. In general, Pm being 0, I'll say a little bit more about that, but there's no obvious statement about Pm being 0 and its constraint here. I mean, Pm has to be rationally 0 for this to even make sense.
Yeah, sure.
Yeah, it's a reasonable question, but I don't know of a simple answer. Okay. So let's now, rational homology spheres, and in fact, two connected. So for the remainder of this talk, I'm going to talk about how to classify two connected 7 manifolds with the invariants that appear. In particular, I'm going to talk about new work where we work out how to define this invariant. Actually, before I head on, let me just make a remark. So M admits full holonomy G2 implies, this is a theorem of Joyce actually, that this is non-zero in the fourth column. So if your goal in life was to maybe find homeomorphic but not diffeomorphic G2 manifolds, or you wanted to classify them, you'd be out of luck because the existing invariant is not defined. So these homotopy spheres are floating around, but you don't have an invariant to see them at the moment, necessarily because Joyce will tell you in the full holonomy setting that the contrarian class is non-zero. So that's the background for what's going on now as we talk about classifying two connected 7 manifolds.
This is in rational homology.
Thank you. Thanks very much. So, a rational homology sphere, the thing that's going to dominate will be the torsion group. If you work out by Poincare duality, this is the only interesting group, and by assumption we have the value of a sphere, so it's going to rationally, so it's going to be torsion. So the linking form is such a map. It's a bilinear pairing. Linking form. And it's suggested. Maybe a revision, but it's worthwhile to say what to do. So you take C of x and you evaluate it against y, you divide by r. Well, what's C of x? So here, imagine these are cycles representing x. So this was x. I know that some multiple of x bounds, okay? So maybe in this case it is 3, maybe 3 times x bounds. So this was, let's say this was a representing 3 guy. This is now this is what I mean by C of x. It's 4-dimensional, and so in general position, it's going to come and intersect y. So that's what I mean by this angle. Count the number of intersections between some sort of generalized Seifert surface, and then divide by what you have to multiply by to get the Seifert surface in the first place.
H3 times H4.
This is correct.
It's 1 H4. Okay.
Yeah, I represented, sorry, this is, thank you, these are the Poincare duals.
Again, thanks. Sorry, right.
The Poincare dual of y will be a 3-dimensional.
Sorry.
Yeah, no, thank you. Okay, so that's familiar. The other thing you have in this dimension, which is a feature of this spin characteristic class, is that there's a refinement. So it's a quadratic form. And it's a refinement in the sense that so, yeah, I think in the interest of time, I just want to, I don't want to go down and write this down. I want to just tell you at a conceptual level what this is. It's an algebraic boundary. So we write M as the boundary of W, and W we assume is 3 connected. Remember, W is an 8 manifold, it's spin, and that actually means that its tangent bundle vanishes over its 3 skeleton. So the basic lemmas of surgery means that there's any topology here on the 3 skeleton, you can just kill it using surgery. So you can always assume that any spin 7 manifold has a 3 connected co-boundary. Now, what are the algebraic invariants of this 3 connected co-boundary? Well, we were talking about them in the definition of the Seals-Kuiper invariant. So there is the intersection form, and there is this characteristic class here. And yeah, so if there's any justice in the universe, there should be some relationship, and in fact, in mathematics, there should be some relationship between the intersection form of W and the linking form of M. Okay? And in fact, you can compute one from the other. And now if you add this PW here, then you get the Q of M. So the linking intersection form gives you the linking form, the whole pair together gives you the Q of M. So I just want to say that the algebraic boundary of this is Q of M. And I want to leave that at the level of explosion, because I don't know that going into the details now will enlighten anyone.
But let's say, just for curiosity, that is not spin. Is this linking form still always defined in this way? Or
This is true. This is true for nothing about dimension 7. The linking form is always defined like this. Right? It's just a definition of the linking form by a Poincare duality. You can define it using the Boxstein homomorphism, and you understand geometrically this is what it means. And here we didn't use spin at all. What we used was the spin fact gave that this was characteristic for that. That's the only point where spin is coming in. There's a certain evenness here, and that's what lets you get this quadratic form. Yeah. Okay. I mean, let me give you an example. If we take these guys here, that I wrote down, these 3 sphere bundles over the 4 sphere, then PH4 of M, this is actually a Z mod N. This is one of the questions that the organizer asked me to provide. And then the linking form, well, I could write it like this. If you work out the sign, it's a minus N. So what that means is that if you take two elements in Z mod N, you can multiply it as a ring and then divide by N. Okay. So that's nice. That's what the linking form is.
What is the quadratic refinement in this case?
Oh yeah, you're going to test me.
I mean, how is it defined?
I didn't want to tell you. It's a black box. I mean, if you know how to define the linking form from the intersection form, you do something similar and then you add this in. I'm just trying to save 5 minutes. So, yeah, one thing that's annoying is that this quadratic refinement is not defined intrinsically. Okay, to define it, I still need a co-boundary. This is something like minus Q in X is something like minus X squared over 2n plus P. Yeah, and thank you for this question, because this, I can tell you one important formal property of this quadratic refinement. It's not homogeneous. Often when you write down these things, I also should have written down that q of minus x is equal to q of x, but that's not what happens. But now our contrarian class comes into the game. This is Bm of x evaluated against P of m. Okay. So P of m is another element in this group. So this is called, with good enough reasons, for homogeneity. So this is my thesis, and it says that if I have two of these two connected rational homotopy spheres, and if I have just a completely algebraic, F is supposed to be algebraic here, if I have an isomorphism between their cohomology groups, so then F is equal to F star of the diffeomorphism. That's if and only if two things happen. One, it preserves this quadratic form. So there's an obvious way to pull back these guys. It's just a function, so you just pull it back. And the other thing you need is that the Eales coefficient invariants agree. Remember, the Eales coefficient invariants are defined if the rational contrary eigenclass vanishes, and that's happening by assumption. The rational value group is 0.
F is a homomorphism or diffeomorphism?
Diffeo. Yeah, sorry, this is smooth. Thanks very much. And yeah, this is pretty subtle, but if you count the bars here, this is my, maybe I'll say this now, that's my, that's a homotopy equivalent, this is a homeo, and this is a diffeo.
What is an isometry?
What's an isometry? Yeah, okay. And if you really want to, you can squeeze in here almost diffeomorphism. We might need that later.
Okay.
And that's a uniqueness, that's a classification statement, but what about realization? So all possibilities are realized, but there's a relationship. I find a rather beautiful relationship. So if I take this Eales coefficient invariant of m, it should be equivalent to the arc invariant of q of m modulo z. And I'll define the arc invariant as follows. So the Gauss sum of q is the sum over all the x in the fourth cohomology at m. This seems like a totally weird thing to do to me. Okay? You've got a number in q mod z, so you can think of that as a complex number. You sum all of these things up, and it turns out that this is the square root. It's always a non-zero number, and it's, therefore you can take its argument. And that's how you define the arc invariant. So these two are equivalent invariants, because this is always a non-zero number, so the arc invariant is the argument of this complex number. And I remember when I discovered this, I thought that was rather nice. That the Eales coefficient invariant is related to this Gauss sum invariant of the quadratic refinement. Okay. Yeah.
When you say all possibilities are realized, it's all new.
Every tune you can think of, and every corresponding value of S that satisfies this relationship you can build.
Okay.
And this is you know, in some sense, I wouldn't be going into this detail. There's a reason that I want to go into this detail. I mean, it's nice to give explicit examples, but it actually turned out to really understand these inertia groups and to really understand these G2 structures, we really had to understand this classification correctly and have it stated very neatly. So, okay, you could say, how much do I care about 2 connected 7 manifolds or whatnot, but to really have this very clean and clear statement was important when we wanted to go on and look at harder problems. So, I've tried to do that now as quickly and painlessly for you as I could.
How about the H4s? All possible?
Yeah, these are all torsion groups. This is the rational homology sphere assumption there is important. So every torsion group, every linking form, every refinement of the linking form is so on. Yeah, so now what I'm going to start to do, excuse me, is tell you about how to handle the situation when the fourth cohomology is infinite, following from Thomas's remark. So now inertia and reactivity. So just remember, if I have one of these spin 7 manifolds, at the moment no 2 connectedness assumption. This is a perfectly good group, subgroup of Z mod 28. I just look at all of the homotopy spheres such that don't change the smooth structure up to a spin diffeomorphism. And as Frank mentioned, there's a couple of, once you have inertia groups, and actually Will Gollinger's, who's here, wrote his master's thesis, a very nice master's thesis on inertia group of 7 manifolds, you know that there's a lot of different flavours of them. So to talk about surgery theory, I want to do the H guy, and here's the M guy. So for this guy here, you should say that this is this F here. This should be a diffeomorphism. So F should be homotopic to the identity. You might say these are 2 different spaces, but no, these homotopy spheres are, in fact, sigma is just the same thing. We'll be using this in a moment. It's nothing but 2 disks glued together with an exotic diffeomorphism. So when you connect some of the homotopy sphere, you don't change the topological type, and it makes sense to talk about something being homotopic to the identity. If you put on your topological goggles, it's just the same space. And the other thing you could do is, well, you could ask that F star was the identity on integral cohomology, for example. And there'll be 2 things that'll play a role. But you could now have any flavour of inertia group you want, given any sort of reasonable constraint you care to put on a self-homomorphism of the manifold. And I'll just, here's a good exercise for you that if you're following along for surgery theory, so in terms of structures, actually, in S diff, I can take M, connect some sigma, and I have this canonical map for identity, right? So that's a nice structure. This is an element in S diff of M. And you could ask, well, is this the same thing as the identity structure? That's the canonical base point that I always have. And that's if and only if sigma is an element of the homotopy inertia group. So that's a good, if you're sort of new to surgery theory and you want to understand the definitions, that's a very good exercise to understand the definitions of the structure set and when 2 things are the same in the structure set. Yeah, but in general, there are obvious inclusions here. I've drawn it in the wrong way, haven't I? Okay. So this includes into this, includes into that. These inclusions can all be made proper inclusions. So there's no reason for these different flavours of inertia to be the same. So, my blackboard technique is failing me, so I'll just grab this board here. So I've used this word before. There's a number of different ways to define an almost diffeomorphism, but this is the simplest one for our purposes. So a diff of M, this is by definition diffeomorphisms, everything's in the spin category of what I'll write as M bullet. So that's M, and just take out a small little open 7 disk. So it's the spin diffeomorphisms of M minus the disk. And this is, I want to finish here, so we'll bring in the basic, the fundamental lemma, how you can compute an inertia group. So there's an exact sequence. So just think of, this is pseudo-isotopic, just think of that as the space of connected components of diffeomorphisms. Simply connected 7 manifolds, you won't go wrong. And then there's a singularity homomorphism here. So what would you do with an almost diffeomorphism? You would restrict it to the boundary and build the corresponding homotopy 7 sphere. Okay. And we'll call that sigma f. And obviously, if the thing you get, well, not obviously, it's a deep result of surf and Smale, but if the thing you get here is the standard sphere, then in fact you can pull back from here to an honest diffeomorphism. You can extend your strange diffeomorphism. So let's draw the picture. Here's M, here's M, here's boundary of F, here's dash. To extend to an honest diffeomorphism, I would need the thing on the boundary to be pseudo-isotopic, to be identical. And that's what this sequence encodes. But now, all right, how do I evaluate this? It should have something to do with mapping tori. So, okay, if I had such a diffeomorphism, how would I actually work out what this homotopy sphere was? Well, we know that this Eales-Kuiper invariant is a complete invariant, so it's enough to compute the Eales-Kuiper invariant. And this you get by taking the mapping torus as a spin manifold, because it's a spin diffeomorphism. You can take the square of that and evaluate the mapping. Okay. So I'm going to beg your indulgence for 2 minutes, since I believe I started 2 minutes late. I think I'll push on for 2 minutes just to reach the key definition. I mean, this is a nice exercise. If you think about the mapping torus, so I want to just give you, I'll just say a few words about the proof and then I'll make a definition. What you should do is you should take the mapping torus. So that would be the all of M cross I, and then you do the usual thing. You take M0 and you would identify it with F of M at 1. But remember, F is not defined on the whole manifold, it misses this little disk. So that when you glue up in this picture, you're going to have a singularity, right? Yeah, that's the picture of the mapping torus. And exactly what you have here by definition is this sigma f. So this mapping torus is going to be your co-boundary and you can compute with the Eales-Kuiper invariant. But now Novikov additivity, oh maybe I had to normalize this, divide by 8. Now you just look up, this is a co-boundary, and you remember the formula for the co-boundary is this thing here minus the signature. But the signature of a mapping torus is 0 by Novikov additivity or whatnot. So that's nice, and that now leads you a sort of a key invariant. If you want to know this inertia group, so here's the definition of reactivity. And that is, we use, so R of M is a non-negative instance defined by the following equation. So P squared of A div is this. Right, so you look at all the possible squares of contrary eigenclasses you can get from mapping to array of almost diffeomorphisms. And signature TF equals 0 and PTF characteristic imply that in fact you get 8 times the integer. Signature and the square of a characteristic element agree modulo 8. That's Vanderbilj's lemma. So, yeah, that's sort of, we're halfway through the story of classifying two connected 7 manifolds, and we've just introduced one of the key suspects, which is reactivity. Thanks.
And the set of values from gets is a subgroup because if you do f twice, it just adds.
It is an additive, yeah, that's right. It's a subgroup.
In part 1 of that lemma, I expected the sequence to carry on and
okay.
to the inertia group in theta 7.
Sorry, to
map to the inertia
oh,
group.
yeah, that would be a better way to do it. That's a very good point. Yeah, thanks, Oscar.
Sorry, not the inertia group. To map
Yeah, no,
to
this was not the optimal statement. So in fact, we can keep going here. By definition, what you get here is the inertia group element, which is a key point, and when that goes to well, maybe we just put a 0 here. So the things that you get out of this are all the possible homotopy spheres.
That's not what I meant. I think I meant mapping to theta 7 like you had, and then that acts on the structure set of M.
Oh, okay. All right. Yeah. Sorry. That's a good exercise. So I don't know. Maybe that's right. But let's just say the image of this singularity map. This is a good exercise that the image of singularity is equal to inertia group. And if for the actual structure set itself, then I think we'd have to do everything with homotopy inertia groups or whatnot. That's the tricky thing.
Yeah, okay.
So we'd have to look at these things homotopically identical.